is work, energy. Then we will be discussing about the relationship between work and energy. Then we go to conservation of energy. Then momentum. Have you heard of momentum before?
And just like the force, like
Yeah, that's right. Okay, so we'll be discussing about momentum, the impulse. You may not know what impulse is. Then finally the conservation of momentum if time permits. All right. So let's start with work. What is work?
energy applied to move.
Yeah, that's right. Energy applied to move something. All the time we are working. I'm talking, that's a work. You are listening to me, that is also a kind of work. And he's adjusting the camera, that is also a kind of work. So whatever we do, we need a force. Suppose I'm lifting this bottle. I'm applying a force on top of this. So, work can be expressed as energy which is transferred by a force, or in other words, work can be defined as the force which is moved to displace a certain particle from one place to another. Okay, so you don't have to write anything, all the notes are given in the worksheet. So I'm briefing you out of what I'll be teaching you today. So do you understand what work is? I don't see. Yeah.
What are you looking for? Primary marker?
No, not the marker. Okay, okay, here it is.
Yeah, that's
Okay.
Wait, so like when you're talking, like what is the object and what is it being applied to?
Sorry?
When you're talking, it's
Yes.
a work, right? So like, what is the object and
Our vocal cords,
okay.
our tongue, mouth, everything, whatever we do, there is a force involved.
Mhm.
Okay? So even if we breathe, this is the force involved. Understand? So whatever we do, there is a work involved and a force involved. So definition of work is work done is force which is needed to displace a certain particle from one point to another. So if you look at the note, you will see that the work is described as a force which acts on an object to move the object from one place to another. Alright, so let me draw an object.
Mhm.
I'm applying a force on it. A force whose magnitude is large enough for it to move. And it's moving. Let's say that the displacement is d. The displacement is d. Now it was here, and after the application of the force, now the object is here. Alright? So, work is, now you know the definition of work is expressed as force into distance, or let's call it displacement. It's not a distance, it's displacement, because distance is a scalar quantity while displacement is a vector quantity. I hope you know it. So displacement of the point of application in the direction of force. This is very important. Displacement of the point of application. This is the displacement of the point of application. This is the point of application. So actually we are finding the distance from this place to here in the direction of the force. In the direction of the force. So if it is the work is this is force into d. So what would you think the units would be?
Meters,
Force is
joules,
Newton.
oh, okay.
Distance is in meters. So it also can be expressed in terms of joule. You may have heard this. Alright. So this is not the only case. This is not the only case. If you want, you can draw this.
So if somebody's pushing on a wall and it doesn't move, it wouldn't be work, right?
That is a work. That is, if it doesn't move, there's no work done.
Okay.
If it doesn't move, there's no work done. Now I'm going to talk about that now. All right. Now I'm pushing on this. The force is in the same direction as of the displacement. Now what would I think if I increase the direction of the force? What do you think? I'm trying to exert the same force, but look at the displacement. Does it displace in the same rate, at the same rate? No, it doesn't. It gets slow and slow. And what do you think when I make it perpendicular?
Stop moving.
It does not move. So that's why I said the direction matters. The direction matters. Okay, so let's consider a common scenario. Okay, let's take this one. Now I'm going to use the same object, but I'm going to apply the force in a different direction. So this is the common case. The angle between the force and the horizontal is theta. Now how shall we write it? Still we have the same definition. Work is force into displacement of the point of application in the direction of the force. Okay, so this is where it is now. Do you think that we can use the same F? Do you think that the same F that we used in the first example can move the object from here to here? No, it does not. So it is its horizontal component which is moving it. You saw it. That's why it got reduced. The rate of displacement got reduced. So we must first find out the component of the force in the horizontal direction. So it now becomes, can you tell me what it is? F cos theta into d. Do you know this one? Do you know about cos and sine?
yeah.
Do you know about cos and sine? Okay, so I can understand, I can feel that you don't know how to get the resolutions of the forces. Okay, let me quickly explain that to you. If this is the force, every force has two components. Every force can be divided or resolved into two perpendicular components. This is the perpendicular one, let's call it y, and this is the x. And if this angle is theta, the horizontal resolution of the force is F cos theta. Remember it like this. This is how I remembered when I was small. I'm closing it. Closing cos. F cos theta. And this is theta. And still your theta is here. Then the other side is sine. So remember one. F sine theta. This was the easiest way for me to remember. If you are closing it with that particular angle, is F cos theta, close cos theta. The other side is obviously sine theta. Now do you understand how I got F cos theta? Okay, so finally we can write this as F d cos theta. Okay, so can you quickly draw this figure, because the equation is given. The equation is given. You can quickly draw this figure, and if you want, you can quickly write it down wherever it is, wherever the space is. And in the workbook, I think it's given as x. Yes, it's given as x, so I will simply mark it as x, and I will make this x. And also for your reference, at a side, you can also draw this. So simply remember that work is force into displacement into cos theta. So while you write, you listen to me. Have you finished writing? While you write, okay. Now, what happens when theta becomes 0? Cos theta, cos 0 is 1. So you get the full work. When it is 90, this is
0.
0. So you saw that when you apply a perpendicular force, it doesn't work. So there's no work. So simply the question that you asked about pushing on a work and wall and whether there's work or not, there's no work. Because it's not moving. We are doing work, but that work is, that force, we are applying a force, but that force is not large enough for the wall to move.
So there's nothing being displaced.
Yeah, nothing is displaced, no work done.
Okay.
For a work done, there has to be a displacement. Okay, and one other thing. At the end of that part, you will see that we are talking about a graph. The graph is force versus displacement. The graph of force versus displacement gives you, the area beneath the graph of the force versus displacement gives you, what do you think?
That's the work.
Okay, so you can get a quick switch here. Alright, now that's about work in the most concise form. And let's start doing the sums. Can you do the first one? We have a couple of sums here. So you can make use of this space to do the sum. I want you to do the first one.
Then just 400.
Yeah, and you have to write the units. Units is a must.
Can I write in joules?
Yeah, no harm. Joule or no, don't write joule. Just write J. We don't usually write the full name. Okay. That's right. Okay. Now I want you to go to the. Skip the second and the third. I want you to go to the fourth one.
How do we know the force applied?
You lift an 8 kg box. A good question. You lift an 8 kg box from the floor to a height of 2 meters above the floor. Let me do it. Let me give you a hint, then you will know afterwards. Now, we have a box. We are lifting it up. We are lifting it up. What is acting against us? Its own
It's
weight.
Yeah, weight.
Its own weight. If you lift your backpack, you will feel the weight. So that's going to be the. So against what are you going to do the work? So I'm going to lift. I'm going to try and lift something heavy.
Gravity?
So yeah, I'm working against gravity. So this is hard for me. This is heavy. I'm working against gravity. So what would be my force? The force acting on this chair from gravity.
Okay.
Understand? So what would be your force then?
Wouldn't this be 8?
Your force would be the weight. What is weight? Weight is mg. Do you understand? So let's use F equals, work equals F d cos theta. Okay, so this is, we are moving it up. And this is the weight mg. Weight is mg and this is mass. You know that. You know that? Yeah. Okay, so what is the force? mg. And what is the distance?
2 meters.
2 meters. So it's simply, how much is m? 8.
8.
G, let's take it as 10. The precise value is 9.81, m is minus 2.
Okay.
But for the moment, we'll make it as 10.
Okay.
10 and D is 2.
2.
So how much would this be?
160.
80, 160 Newton meters or joule.
Oh,
Okay? Understood?
Right, so I really don't get the mg part.
Okay, right. Now once again, this has a mass.
Yeah.
The mass is, let's say, assume it's 1 kg,
Mhm.
1 kilogram. This is being pulled by gravity.
Yes.
That's weight. So mass and weight are two different physical quantities.
So mg is mass gravity.
Sorry, mg is
Mass.
the gravitational pull of the mass, which is called the weight.
So it takes the weight times
Yeah,
10.
that's right. mg is a force. M alone is not a force.
Yeah, exactly.
Understood?
Yeah.
All right, now let's go to the next one. And whenever you get a question, please make it a point to draw. Even now I draw.
Yeah.
Yeah, so carry on. So yes, you're almost there. Can you simplify it? So I hope these are multiplication.
Yeah.
Okay, yeah, yeah. Do the simplification.
Times with 3
How
over
much is
2.
cos 30?
Root 3 over 2.
Yeah, root 3 over 2, that's right. So let's not simplify it, let's keep it in the form as the simplified form. Okay, for the moment.
So it would just be 5,000 root 3, right?
It has to be, yeah, that's right, 5,000 root 3
Yeah.
j. That's right, good. So please remember. Now, this is a place that some kids confuse themselves.
Okay.
There are so many kinds of forces, and we were talking about the mass and the weight. So weight is acting here, okay? But the displacement is in this direction. So would weight interfere with the force? No, it would not. Okay, good. Now I want you to go to the last one.
Wait, so we didn't have to use weight because they already gave us the force? Because they already gave us the force applied?
But there is, or to confuse you, the weight is also given, the mass is also given.
Okay.
Did you see it at the beginning?
Yeah, I saw 30 kg.
Yeah, that's right. So there are sometimes in some questions there are data which are actually not wanted.
Okay.
They are for you to, they want you to, that's to confuse you. That's how it is.
Okay.
Okay? So I just pointed out a place where most kids go wrong.
Okay.
For that, since we don't,
I don't know the cosine.
never mind, you simplify it as much as possible with the cost value.
Okay.
You can go home and simplify if you want. Yeah, so it's 80 cos 25 joule, that's right. Good, okay. Let's move on to the next section. So, if you read the second objective, you will see we are trying to apply relationships between work, net force, displacement, velocity, kinetic energy, and to solve a variety of problems. Okay, so under that, first we will talk of gravitational potential energy. Okay, what is energy? Before we talk of gravitational and potential energy. You are jogging, you are running. So what is it? Would you think you would have the same energy to run in the morning and the evening after work? Do you think would you have the
No.
same energy? No.
No.
So what is it? Energy is the ability or the capability of a person or object to work.
Okay.
Okay, so I think it's there. No, it's not there. So in the space given, you can write that energy is the ability to do work. Simple as that. So there are various kinds of energies. Can you think of energies? Yeah, solar energy, chemical energy, then wind, sound, then what else? Light, potential, kinetic, that's right. So there are so many kinds of energies, but in mechanics, we are dealing with mechanical energy.
Okay.
So that's not there in the note, just keep in mind. Mechanical energy is energy which can do a mechanical work, which can move a certain object from one place to another. That's the kind of energy that we'll be talking about in mechanics. Alright?
Is it in joules?
Yeah, of course. I'm coming to that. So, I told you there are two kinds of energies. Several kinds of energies. One is mechanical energy, and under mechanical energy, there are actually three kinds of energies. One is kinetic energy. The other one is, I will write KE.
Yeah, sure.
Okay. Then you have potential energy, and I was talking about another one. The other one is, actually we are not doing it now, it is a subdivision. One is gravitational potential energy, and the other one is the elastic potential energy. So we are not talking about elastic potential energy at the moment. Elastic means you stretch things. So the kind of energy that is stored in by stretching things is called the elastic potential energy.
Like rubber band?
Yeah. So we are not talking about that later. That's a completely different subject. Okay. So what we will be talking about is the kinetic energy and the gravitational potential energy. Okay. So so I said energy is the ability to do a work. So suppose I have an energy of 100 joules and I'm making use of that to work. So work and energy would be the same. It has kind of a close interrelationship which cannot be very well explained. Understand? And therefore energy too has the same units, and sometimes when we describe work we use Newton meters, but not for energy. For energy it's joule always. Okay? So under that, now first we'll talk about gravitational potential energy. Gravitational potential energy is the energy which is gained by an object which is when it is moved against gravity. When it is moved against gravity. Suppose we are moving this up. So work is actually energy. In other words, so F d cos theta. So what do you think the force is now? We talked about this in one of the sums. What do you think the force is now?
On that
We are
example?
acting against gravity.
Pulling.
So if this is, that's right, the gravitational pull. So it's simply mg.
Oh, yeah.
Okay, it's simply mg. And if this distance is h, height, which denotes height, and there is of course no theta, because it's in the
Straight.
direction of displacement, so cos theta is
Right.
1. Cos theta is 0, this is 1. So this is mgh. So potential energy is as simple as mgh. Okay? Alright. So actually these are not vector quantities. Energy doesn't have a direction. You can't think of a direction of an energy or work. But when it is potential energy, we use a plus and a negative sign. The reason is we always assume a potential energy 0 level. I will write it in short. Potential. This is not very important for you, but for your reference, for your future reference, this is the potential energy 0 level, where we assume that the potential energy is 0. So with respect to this point, we are calculating H. So if we come now, suppose you have a well here. Suppose this falls down. Then what will be the displacement now? It will be negative H or negative H dash. Then potential energy will be negative. But it is not the same idea that you get from a positive vector and a negative vector. Understood? Alright.
Wait, so can energy, like for example, like the sun, when it emits like a beam of light,
Yes.
wouldn't that be like a vector almost? Because it's like, it's going a direction.
Yes.
So that'd be kind of, wouldn't that be an energy? Like,
Yeah, of course. It's radiation. Radiation is a kind of energy.
Okay.
So everything is based on the energy that we get from sun.
Okay. And you said mechanical energy is like ability to work and move, right?
Yeah, yeah.
So potential energy wouldn't be mechanical energy?
Sorry?
Potential energy, it wouldn't be mechanical energy, or?
Yeah, of course. Why we are moving it up.
Okay.
And due to that movement, it is attaining a certain kind of energy
Okay.
due to its position. Understood? Okay, so now, why don't we start doing the next sum? Calculate the gravitational potential energy. Yes. 1 minute. Thousand, that's right. Move on to the next one. A child is about to slide down a slide with total length 4 meters. The length along the slide is 4 meters. The slide forms a 30-degree angle with the horizontal.
But the angle doesn't matter, right?
Hmm? Why don't you draw it? Then you will understand. Draw it. Drawing a figure won't do harm. It will help you. It will help you to understand the question. So it is, what they're talking about is slanted slope like this. And let's hope this box is the child. And he's being pulled by, I think, yes, he is trying to slide down under the action of gravity. Okay. And what are they asking of? They're asking of the gravitational potential energy of the child before he started sliding down. So this is mg.
Oh,
Okay.
so the angle doesn't matter.
Yeah, so you don't even have to use that equation. Just write that potential energy is mgh, but we have to remember one thing. This is the potential energy zero level. So with respect to this level, you are measuring the height.
Okay.
Okay, so how much was it?
1,000.
Uh-huh. Let me see. This is the length of the slide, and this angle is, this question is a little bit a tricky question. It doesn't give you all the data directly.
Okay.
So mgh, we know m is 25, g is 10, and do we know h? We don't know h, but we know the length of the slide, and we also know the angle here. So what do you think that this h would be? Using that cos value, what do you think it would be? It would be 4 cos,
Oh, okay.
how much would this be? 60.
Oh, okay.
Understand? So this length would be 4 cos, h would be 4 cos 60.
It's just 3069.
That's right. So the final answer would be 500 joules. Understood? Okay, now are you okay with that? Yeah, now to the last question. I'm going to give you only 1 minute. It has many details, but you don't need all of them. You need only 2.
What is a 125 Newton box? Is that?
That's the weight of the box. If a weight of a certain object is described in newtons, that means its weight. If it is given in kg, then it is mass. So if it is given in newtons, you don't have to convert it by multiplying it by 10.
Okay.
You simply use it as 155. So what I would suggest, what I would always tell my students is, whatever it is, draw the diagram. You don't have to draw the diagram here. Write the equation. Always write the equation. It helps. It will take 1 or 2 seconds, but it's going to help you. M, G, H. Write this one. Now move on. Don't start thinking without write the equation.
Wouldn't it just be the height is like 0?
No, the box is being pulled from the bottom to the top. The question is what the potential energy is at the top.
So it would be 1.8. So 155 times
Yes,
1.8.
that's right. Yeah. So write the equation and you can simplify it at home. Okay, so mg is 155, okay, and h is 1.8. There are so many other unwanted details which are confusing you. Okay. All right. Now turn to the next page and we have an interesting question. Which situation describes a system with decreasing gravitational potential energy? With decreasing, underline that word, decreasing gravitational potential energy. Let's read them. A girl stretching a horizontal spring. A girl stretching a horizontal spring. It's horizontal. That word is important. A bicyclist riding up a steep hill. A rocket rising vertically from Earth. A boy jumping down out of a tree onto the ground. What do you think? So we are dealing with gravitational potential energy. They are asking when does the potential energy decrease? Potential energy, you know, increase when you go up. It doesn't decrease. It decreases when it comes down, when something comes down.
So it'd be
Okay?
D.
It should be D. So why is the first one not an answer? A girl stretching a horizontal spring. I told you with a spring you are dealing with another kind of a potential energy. Forget it. Still you get a kind. The important word there is horizontal. You are stretching it horizontally. That means you are not doing any work against gravity. Understand? So that's out. A bicyclist riding up a steep hill. You are riding up, that's out. Your potential energy is increasing when you go up. And the rocket rising vertically from Earth, the same way, the same scenario. And the final one is the boy is jumping down. So he had gravity when he was at the top, and when he's down, you know that our potential energy zero level is at the bottom. Okay, so that's the answer. Now let's go to kinetic energy. What is kinetic energy?
Energy in motion.
Yes, that's right. So we have a kind of an equation. I think I derived it. I don't know whether it will be it would be very important to you, but I'll show you the relationship between the work and the kinetic energy. All right, consider a horizontal box which is having a displacement of d and a force F is applied on it, and assume that initially its velocity is 0, and after a certain time when it goes a certain distance the velocity it attains is v. Okay, so I'm starting from work. Work is F into d. We don't consider cos theta because it's horizontal. Okay, work is F into d. And from Newton's second law, have you heard of Newton's laws?
Yeah, but I don't remember.
Yeah, okay. So Newton's second law simply says that F equals ma. You will, in the future, you will learn about Newton's second law in a much concise, in a much more descriptive way. Just remember that Newton's second law is F equals ma. So from this equation, you know that F can be represented as ma into d, man. It's actually not man. So now, my purpose is to find a relationship between the kinetic energy and what we are doing now. So what I'm trying to do next is I'm going to make use of another equation to find this velocity here. Let's make use of equations of motions. You may have done this before. V squared equals u squared plus 2as. Have you done this before?
No.
Equations of motions?
No.
Okay. Assume that there is an equation like
Okay.
this. Okay.
Should I memorize it?
When you do them properly, you will have to memorize them.
Okay.
There are 4 such equations. When you do sums, you will automatically memorize them. So from this equation, we know that initial velocity was 0. So this is 2a. S means how much? D. And a is acceleration. You know acceleration?
Like speeding up?
Yeah, that's right, speeding up. So v squared equals 2ad. Now, what am I going to do? Now I'm going to make use of the a I have here. A equals v squared over 2d. Do you understand this?
Yeah.
And now I'm going to substitute it to this place. So this becomes a v squared 2d and d. And you can see these are all multiplications. D gets cancelled out to this d, and you get half mv squared.
Oh,
Okay? So this is work. What is work? In other terms, energy.
okay.
The work we use to move this object from this place to this place. In other terms, the work, the energy which is causing an object to move, kinetic energy. I will write it in short. Understood? So this is how this is derived. So I don't know if you want it, you can take 30 seconds because we are kind of running out of time. No, time. Don't say the time properly. Never mind. Take 30 seconds and write this one if you want. And you can write here, or this, you can write equation of motion. So I think we'll be discussing about this when we do rectilinear motion in the future.
Wait, what was that motion again? Rectilinear.
Rectilinear. Rectilinear means we have circular motion.
Yeah.
We call it angular motion,
Yeah.
and the linear motion is all known as rectilinear motion. You will learn them in the future. Don't consider those words much. It will confuse you. Okay, now we are at what kinetic energy. We know that it's half mv squared, and so as I told you before, it is also a scalar quantity. And if you have lots and lots of particles, like a whole system of particles moving together but in different speeds, then for the kinetic energy of the whole system will be, you can see in this equation, it can be written as half m1 v1 squared, half m2 v2 squared, and so on.
What is that used for?
Assume that we have a system where there are so many particles of different masses which are moving in different velocities, and if we want to compute the kinetic energy of the entire system, this is how we do. This one has no sign change, whereas there was in the potential energy.
Okay.
I was talking about a negative potential energy, but there is no such potential energy. Because there can be a change in the velocity, but when it is squared, it becomes positive. All right? Okay. So now let's move on to the questions. Can you do the first one?
Can kinetic energy be, it can be zero, right?
Sorry?
It can be zero.
Yeah, of course. If it's not moving, it can be zero.
$40,000 times 250.
Okay, there is a certain thing I have to tell you there. Did you see a difference? Did you note anything in that question? A 500 kg race car is moving at 200 kilometers per hour along a straight track. Now we know the SI units are meters, seconds, and what is the other one? Kilograms. But here the velocity is given in kilometers per hour. So number one, the first step should be you should convert that into,
meters.
that's right. Okay. Do you know how to do it?
Is it just multiplied by 1,000?
Yes, multiplied by 1,000 and okay, I'll do it. Okay, so this is the way. Okay, per hour. Per hour means I'll put it here.
Okay.
Okay. Now I'm going to make this into meters per second. What should I do to convert the kilometers into meters?
Multiplied by 1,000.
Multiply by
1,000.
1,000. That's right. What should I do to convert an hour to seconds?
Divided by 60.
How many seconds do you think that an hour has?
Wait, divided by 3,600.
That's right, 3,600. Okay? So it's simply, so I'll cancel this 0 to this 0. Remember, I'm not going to cancel these two zeros. I'm only dealing with these two for you to show a shortcut. So it will be 200. So this is 2 times 5, 2 times 18. So if you multiply it by 5 over 18, you would get the value.
Okay.
Okay? So you write it down. I'll do the sum for you. So the kinetic energy is half mv squared. M is 500 v squared. Now 200. I can even simplify this a little bit more. So this becomes 2 times 9, 2 times 100. So this becomes 500 squared over 9 squared. So it's a long multiplication. So you can do this at home.
Okay.
So all what I want you to is to have an idea of the concept. Okay? So this will be something which you do you understand now?
Yes.
So you have to be always keep an eye on the units. Okay, now I want you to do the second one. Of course, I am going to do that because it's a little bit a complicated sum. Let's read it together. The International Space Station, around 990,000 pounds, completes 15.54 orbits around the Earth every day, and on average maintains an altitude of 237.5 miles above the surface of the Earth. Okay? So to do this sum, you need a little bit more knowledge, which I'm going to do now. Okay? Right.
So on this one?
And do you have an idea of how to do this? Yeah.
No, I was just wondering if you like convert this to kilograms and.
No. Because we also have a system called the CGS systems, where you express terms in other units too.
Okay.
So let's leave them as they are,
Mm.
okay, without trying to convert them.
Mm.
And I want you to understand the concept. Okay. So this is the Earth, this is the orbit, okay, and this is whatever the space station is, and it is being, this is mg, and in the future you will know that there is a centripetal force which is acting on them, so which balances it, okay, which occurs as a result of its circular motion. You will learn them later, not now. Okay, so don't consider those. Now, whatever the energy this has is mgh, is it? That is the same energy that is using to move around the Earth, simply to move around the orbit. Understand? So, this mgh is equals to half mv squared. Do you understand?
Yeah.
So m get cancelled. So we have this, okay, I'll write m square here. Then you can take 2 right here, it becomes 2gh. So what would we be? Square root of 2gh. Okay. So we have, I think, about 1, 2, 3 data, out of which we need only 1. Okay. So it will be 2, let's take 10 for g because we don't know the gravitational acceleration in other units.
Yeah, 237.
And by some means you have to convert 237.5 into meters. Okay? Understood? Alright. So this sum is confusing because it's giving so many other details actually which are not wanted. So that's how the sums come.
So is V equals root of
Root, yeah.
2gh a formula that, or I just had, is it a formula or?
Yeah, we have a separate section in mechanics where we talk about the gravitational pull and the gravitational fields, in which we will be discussing about them, and while we discuss them, we are deriving this equation so that you will be memorizing this equation. Okay? But for the moment, this is how you do it, if you don't know that, and even if you forget it. Okay, so let's skip the last one and keep it for you to do at home. And planning to go to the 3rd page. The work energy theory. What does this mean? Now you know, if an object or system has work done to it, a change in energy occurs of the same magnitude. It could be an increase in kinetic energy or potential energy. That is, if you do some work, such as by lifting this, whatever the change. Now, suppose my potential energy zero level is way down here and it was here. And this has some kind, now this is at rest, but it has a certain potential energy. Now I'm lifting it up. I'm doing some work against gravity. And this is attaining some kind of an energy into it. So what is that? A potential energy. You can see there's a change in potential energy.
Okay.
Alright? And if I by some means push this up in a certain acceleration, what do I get? I get 2 kinds of energies. There is a change in the potential energy as well as a change in the kinetic energy. The velocity of the object was 0 here. And obviously, this has a velocity now. I'm moving this up, so it is gaining a potential energy. So whatever the work I did made a change in the potential energy as well as in the kinetic energy. Understood?
Yeah.
So that's what it means by this sentence. If an object or a system has work done to it, a change in energy occurs of the same magnitude. this could be an increase in kinetic energy or potential energy. Of course, an increase in kinetic energy and potential energy. So it can be expressed as W equals delta U. U is actually a term we use sometimes in chemistry too, to denote the term energy. Okay? Alright, so this is a very typical equation that we come across in chemistry as well. Okay, so keeping that in mind, I don't want you to draw anything there. If you want, you can simply draw two objects, assume that it is moving here. You can see that this has v1 velocity here, and by this time it is attaining v2 velocity. So the work done is equals to the change in the kinetic energy. Understand? And you draw it. Then when you go home and look at this, you will understand what I talked about. And suppose you are moving this up, and now this distance is h. This was a table, and the work done is now delta potential energy. Understand? This is h1 and this is h2. Okay. All right. Let's quickly do the first one. A chef pushes a 10 kg cart from rest a distance of 5 meters with a constant force of 50 newtons. Ignoring friction, determine the cart's change in kinetic energy and its final velocity. So using the above equation, work energy theorem, what can you write? Write that equation. W equals delta U. Now think about what kind of energy you are dealing with. Is it kinetic or potential?
Well, when it was at rest, it was potential, and then
Yeah.
it moves as kinetic.
Yeah. Now, it doesn't say that the cart is slanted, on a slanted flow. So we have to assume the cart is on horizontal flow. Therefore, it has no change in potential energy, but in kinetic energy. Okay. So it will be delta KE.
Okay.
Okay. So initially it was at rest. After a certain time, it attains a certain velocity. Okay, I'm helping you.
So it'd just be 50 times 5.
Yes, yeah.
And then,
Why don't you do it?
when it was at rest, it would be just 0. Right?
Yes.
So it would just be 250.
Yes. And what would that be equal to? What would that be equal to? Okay, I'll do it. So this is the kinetic energy. So work done. So all right. So what is the work done? 50. It's FD.
50 into.
50 into 5. That is 250.
Yeah.
Now, this is work equals delta KE. So, delta KE is how much then? 250. And we know initially didn't have any velocity. So, what is the change in kinetic energy? Half mv squared negative 0.
Okay.
That is now, earlier I had assume I had a certain amount of energy which is 5 joules, and it increased to 10. What is the difference? 10 minus 5, 10 negative 5. So this is the latter one, this is the former one. Do you understand how I took the difference?
Yeah.
Okay, so this should be equal to 250. Okay, so half, how much is M? 10.
10.
And V is the one we want. And and this is 250. Okay? Shall I simplify this right here itself? I can cut this 0 to this 0. I hope you know that.
Yeah.
And v squared equals 50.
So we just root 50,
Root 50 means you can simplify it as
5 root 2.
5 root 2. Got it? Okay.
Okay. Well, for V, what is the unit?
Meters per second. What is velocity? Distance over time.
Yeah.
So, distance. If you don't know the unit, simply find the definition. Velocity is distance over time.
Yeah.
Sorry, distance over time. So, distance is meters, time is seconds.
Okay.
Meters per second. Alright, move on to the next one. Okay, without moving on to the next, okay, never mind. That's a good question, let's do it.
Do you guys want to take a break? It's been like an hour.
Yeah, do you want to take a break?
I can just finish this.
Okay, finish this. I forgot.
That's all right.
A pitcher throws a 143-gram baseball towards a catcher at 40 ms minus 1, at 45 ms minus 1. If the catcher's hand moves back a distance of 6 centimeters to stop the ball, determine the average force exerted on the catcher's glove. Now think about that. This is my hand. This is the pitcher's hand. And he is receiving a ball. And when he receives this, what happens to this? Both of them act as one. And to withstand this, it's moving back. You understand that. Now keeping that in mind. So what happens? Initially my hand was at rest. Now when this is hitting this, now it's moving. Now what am I doing? I'm doing some work. I'm doing some work. My hand was at rest. I'm doing some work. So what kind of a work do you think that I'm doing? Kinetic energy. So the work done by me by moving this hand from here to here is equals to the difference in the kinetic energy of my hand. Understand?
We'll have to convert centimeters into meters, right?
Of course, you have to. Centimeters into meters, of course you have to, yes.
So it'd be 143 times 10 times 6 over 1000.
10 times 6, how did you get a 6?
6 centimeters.
Mm-hmm.
It moves backwards into 6.
Yes, so where does that 6, now first of all, I'm always telling you, write an equation. Write an equation. What should be the equation? What is the concept? Now I was talking about that.
Okay.
The work done by my hand is equals to the change in kinetic energy. You write it down. Then think. Work done by hand equals change in kinetic energy of the hand plus ball. Please remember, plus ball. Now it acts as one system. Okay?
Yeah.
So what is the work done by the hand?
It moves back 6 centimeters.
Yes, it moves back 6 centimeters. We don't know the force. That's what we are supposed to find.
Yeah.
This is the force exerted by it. So it's F. And how much of a distance does it move? 6 centimeters. Alright, so let's make it 6 into 10 to the power minus 2. Do you know how to convert them?
Mhm.
Okay. Right. So what is the change in kinetic energy? Of course, the latter is great and the final one is small. Because this is 0, half m v squared. Okay, so half m is how much? 143 into 10 to the power minus 3. How much is v squared? V is 45
45.
squared. That is discarding that 0. So F would be,
We just multiply that. out.
okay, I'll complete this. So F would be half 12
Yeah.
and 143 into, now I'm
10
trying to simplify
minus-
this, you get 10 to the power minus 1 and 45 square is just a matter of simplification. Okay?
Yeah.
So I'm not going to draw all that. Now do you understand what's happening? So the most difficult part in physics is the difficulty in understanding what's happening. If you know what's happening, then the sum is easy.
On that equation,
Yes.
5 times 6 times 10 to the negative 2. How do I get negative 2 on that one?
This one.
Yes.
So 6 centimeters, you have to divide it by 100 to make it meters.
Yes.
So when these two come up, it is 6 into the 10 to the power minus.
And then 1.
Yeah, yes, those things actually you should know. Now,
Oh, those are, you're just converting it to
yeah,
the-
just convert it.
Oh, okay.
Yeah, you should know them.
Okay.
So 143 is in grams.
Yeah.
How do you convert it into kilograms?
Divide by 1,000.
By 1,000. So
Okay.
simply don't divide it by 1,000. Use 10 to the power minus 3.
Okay.
Get used to that. Okay? Okay, you can take a break. We have right throughout the universe, in our earth, is constant. It is being all the time. It is being transferred from one source to another, one to another. I hope you all know that. So based on that, we do certain things. So you can write down. It's already there. Energy can never be created or destroyed in the universe, so we can keep track of all energies. We can conserve it within our equations. So, according to that, we can understand that.
The picture was here.
You go to the other one. Okay, I'm sorry. You understand that energy before is equal to the energy after. Okay, so then would there be a delta energy? Would there be a change in energy? Delta E? Would there be a delta E?
Yes.
No. If energy can be neither created or destroyed, there can't be any delta E. Delta E is always 0.
Right, so it can be transformed or something?
Yes, always. Always.
Okay.
It is to now look at the light coming from the bulb. It gives us, it's coming from whatever the kind of electricity you get. It can be hydro, it can be whatever it is being converted into light energy, as well as you can hear slight sound energy, and then also it gives us a little bit of heat energy.
Wait, so you're saying that energy is constant and it
Yeah.
cannot... but
Energy is constant.
What about like sometimes you're like you push something with
Yes.
two different forces?
Yes.
Isn't that you're using less energy in something and more energy on something?
Of course, you are using less energy on something and more energy on something. But what I want to tell you is, this is I think what you are trying to tell me. I'm pushing this with less energy. I can push this with a bigger energy. Then what is happening? If I have about 100 joules inside me, and if I'm using 2 joules, 98 will be there inside me.
Um,
Understand?
so you still have the same amount
Yeah.
of energy.
So the 2 joules I had is now here.
Yeah.
Understand? Okay. So I will draw this and show you. This is a very common picture in physics. Suppose you have a ball here. Now what do you have? This is
Potential.
station potential energy. And you give a small portion, it's coming down. This potential energy is decreasing. Then while it is decreasing, what is happening to this kinetic energy?
No.
It's increasing. It's increasing. So when it comes here, it has kinetic energy and zero potential energy. It depends on the place if you consider this as the potential energy zero level.
Mm.
Suppose it has the enough energy to go up.
Yeah.
Now it's increasing. Kinetic energy is increasing and it's decreasing, I'm sorry.
Potential is
Because it's
going
getting slow and potential energy is decreasing. Now do you understand the interchange of the potential energy and the kinetic energy? Okay, so let's move on to the next sum. A lawyer knocks a folder of mass M off her desk of height Y.
Right, so what is the answer to when can energy be conserved?
Oh, when can energy be conserved? Okay, good question. Energy is conserved in isolated systems. So under the definition, okay, I will give you the proper definition. You can write it here. Write it quickly. Total energy of an isolated system, that's the most important word. Total energy of an isolated system remains constant. Okay, so let's consider this system of chair. This has its own energy unless I give it an external energy. So energy of a certain system remains constant unless it is being supplied by an energy from an outside source. Suppose like Earth gets an impact from a meteorite or a big star or something, then our energy is going to be changed. Understood? Okay. So do the first one. A lawyer knocks her folder off. So that's the answer for that. When can energy be conserved? In isolated systems. Okay, so that sum has lots of symbols.
So we can get a numerical value for this one, right? We
Yes.
can.
Yeah. Okay, so what is delta E? The change. That means energy before, sub, energy after, whatever it is.
So basically it's going to potential to kinetic on this one.
Yes. It's the change. It's the difference between the energy before and energy after. Okay, so you can write it. Delta E equals 0. I, of course, would have started it from here. E before, E after. Okay? But since you started from delta E, I don't want you to change that. So delta E is actually the difference between E before and E after. Whatever it is. I will write it like this because I don't know which one is greater and which one is not. Okay, so delta E. So this is simply 0. So what can you say? E before, I'm coming back to the same equation, E after. So what is E before? What is the energy it had initially?
Potential.
So write it down. What should it be?
M times
M times
Y.
M times G times Y.
Yeah, sorry.
M times, yeah, don't forget that. M times MGH. So when you go home today, please write down the important equations in somewhere. Write it in index cards or whatever it is, or paste it on the wall and have them so that you will remember. Potential energy is MGH, kinetic energy is half mv squared, right?
Mm.
So you will remember. Because we are in physics, we are talking about so many concepts, and I know finally you will get confused. So mgy is equals to the kinetic energy, that is half mv square. Okay, so m get cancelled. So what do I want? I want v square equals 2gy. So v equals square root of 2gy. You understand?
Mm. Oh, yeah.
Okay.
Mm.
Can you do the next one?
Okay.
No, I want you to do the second one, the pole vaulter one, by yourself at home. Okay?
Yeah.
Because it's same as that. And let's move to the last one. Not the last one, of course, the one before. A 2 kg block sliding down a ramp from a height of 3 meters above the ground reaches the ground with a kinetic energy of 50 joules. The total work done on the block by friction is approximately what? So this whole sentence is complicating you. So what is number one? Draw a figure. Draw the figure. It will make you understand the question much better. So this is the block. And always remember to mark the data while you draw it. It is at a height of 3 meters. And when it reaches the bottom, its energy is 50 joules. What is the total work done on the block by friction? Yes, energy before and okay. So what is the energy that you had before? What did you have? You had only,
So
yeah,
would
it
be
was not
before it
moving.
slided?
Mm-hmm.
Before it was sliding down?
Yeah, it was like this.
Yeah,
It
so
had-
would just be
Potential energy.
yeah.
Does it have a kinetic energy?
No.
No. So write
2 times
MGH.
10 times 3.
Yeah, don't write the equation first.
Okay.
Write the equation first. Okay, so what I would do, what's your name?
Siddhant.
Siddharth.
Siddhant.
Siddhant.
Yeah.
Okay, Siddhant. What I would do, Siddhant, is I would write E before and E after.
Okay.
Whatever I write, I would write under E before. So what would it be? I know that you have potential energy before, but no kinetic energy. So I won't write anything here. Okay, and what do you have after?
Kinetic energy.
Yes. Okay, I leave it as that. Okay, so can you write for potential energy? It's mgh. Don't try to substitute the values right now. Do it at the end.
Okay.
Okay? Right, now,
1/2 mv squared.
yeah, okay, now what do they say? The total energy, kinetic energy it has is 50.
Yes.
Is 50.
Okay.
And if you try to substitute the values here, you have the value for M, you have the value for G, and you have the value for H. What are we doing?
Right,
What
the
are we
difference.
trying to look for?
The difference? Friction?
Yeah. So this would be simply 2 times 10 times 3. So this will be 60.
Yeah.
And you have 50 here. And you have a void. Do you see that void here?
10.
Yes. So what is that 10?
The,
That is the energy spent on friction.
okay.
Okay, so now let's go back once again, Siddharth. Let's go back once again. So energy after is not only the kinetic energy, but the energy spent on friction. So let's write energy spent on friction. Okay, understand? So let's take it as x. So you have x here, 2 times 10 times
Very good.
3. So 60, 50 plus x will be 10. So the energy spent on friction is 10.
Okay.
Okay? Okay. Now let's talk about the figure here. Mass M1, so you can see, you can have an idea by looking at it. So mass M1 sits on a frictionless surface and is attached by a light string and a pulley to M2 as shown below. What happens to the gravitational potential energy and the kinetic energy to each block when M2 is released from rest? So we know that it's going down. It's moving down. It's moving down. So this is the pulley and this is the string. It's falling down. So let's start from here. What does it have initially? What does it have initially?
Potential.
Yeah, it has potential energy. So it's moving this way. What's happening to it?
Potential energy is increasing.
No.
Wait, no,
Why?
can it?
Yeah, it's
horizontal.
yeah. It doesn't change,
Yeah.
but kinetic energy is
Increasing.
increasing because it's moving. It's
Yeah.
gaining a velocity,
Mhm.
right? Let's stop here. Let's not think about what's happening to this when it reaches the pulley.
Yeah.
It will either stop or it will either topple, whatever it is. Okay. Then let's talk about the other one. It was at a certain level. Now what's happening to it?
The kinetic energy is going up
Kinetic energy is going
and
up.
potential energy is going down.
And that's right. So I will write it as potential energy is constant. Kinetic energy is increased. Here the potential energy is decreased and the kinetic energy is increased. So, Siddhant, this is a complete, a full entire system, one system. So whatever the increase in the kinetic energy, you can see this is a system. The increase in the kinetic energy of this object and this object has been supplied by the decrease in potential energy. Do you understand that?
Mm.
Yeah. If you understand that, that's it. Understood? This is in a whole system.
If that pulley wasn't there and they were just connected by the string,
Yes.
and-
Then it will fall down.
yeah, so if it was getting closer to falling down, the potential energy wouldn't change though?
Now once it starts falling down, of course it will be decreasing.
Mm-hmm.
It will start decreasing like the same way that it was decreasing for this.
Okay, but like the motion of getting closer to falling down, it doesn't change at all?
No,
Okay.
because it's moving horizontally.
Yeah.
Okay? Alright, let's go to the fifth objective. Analyze the relationship between work done on or by a system and the energy gained or lost by the system. Okay, so read the question. That's a question. We are going to try to do that using a question. The work done in accelerating an object along a frictionless horizontal, underline that, is equal to the change in the objects, is equal to the change in the objects what? There is a horizontal, something similar to this, horizontal object, which is being moved, being accelerated by a certain force. So,
Or be velocity?
oh, yeah, is equal to, probably the velocity is changing, that's true.
Okay.
We are not talking about something which is proportional.
Okay.
If the question said proportional, then you're correct. So when the work, it's proportional. But we are talking about something which is equal.
Is it equal to the change in the objects?
Objects what? What does change? What can you discard first? There are certain items that you can discard.
Momentum and velocity?
Yeah, momentum out, velocity out. There's one more you can discard. I ask you to underline a certain word.
Oh, it wouldn't be potential.
Yeah,
Okay.
it won't be potential, so it's kinetic. So sure, of course you should be able to understand when it is accelerating, the work done is equals to the energy given to the system or to the object, which is being used to increase the kinetic energy of the object. Do you understand?
If it said the work done accelerating an object along a frictionless vertical surface, could
Yes.
it be potential?
Along a frictionless,
Vertical.
of course,
Okay.
of course. It's actually vertical would be quite highly unlikely. It can be a slanted. If you say slanted,
Mhm.
that would have been much better, because vertically it will, of course, vertically it won't slide. It will fall down straight
Yeah.
away. Okay. Yeah, good question. Let's go to the next one. Now we are going to another one, another important physical quantity. Momentum. What is momentum? Yes. Now, of course, we don't have a proper way to describe what momentum is. We have an equation. All what we have is equation. But I will describe it like this. Suppose I have a kind of a clay, or what do you call them? A clay dough that the kids play with, a ball of clay dough here. And I have two different objects, one heavy and one light. And I'm trying to, suppose this is spongy and elastic. And I'm trying to throw this erasers, a small one on it. Okay. And I don't have a heavy object. Suppose this is heavy. I'm going to put it on this. Can you see the impact on it? There was a less impact from the smaller object, which was less heavy, and more impact from the heavy object that we assume that this is heavy. It had a big object, big impact. So momentum is a kind of that unpleasant feeling that you have when you are encountering with somebody who's heavy, and somebody with respect to somebody who's not heavy.
What about like when you're running a race and you suddenly stop but you keep on going? Like when you finish the race, you try to stop your momentum from
Yeah, that's right. You try to stop your momentum. So what happens? You need to exert a force on yourself.
Yeah, so you
And as a result of that, you have to run a couple of meters.
Yeah.
Do you understand? And when there is a collision of cars, you can see the momentum that has caused the damage.
Mhm.
Understand? Okay, so this momentum is defined as you can see in the text, can be defined as the product of an object's mass and velocity. So simply it is mv. So the symbol for momentum is P equals mv. It is given in the text. P equals mv. So P, if you have a simple P, not a capital P, the uppercase P is given for power. So if you have a lowercase p, it is mv. So it is the product of mass into velocity, and you can see that mass is not a scalar quantity, is a scalar quantity, and velocity is a vector quantity, as therefore momentum is
Momentum is in P.
Yeah, momentum is P.
Mm.
Yeah. Therefore, momentum is it a vector or a scalar?
It's a vector.
Vector quantity. Okay, it's a vector quantity. So whenever there is a momentum, please have in your head that it has a direction.
Mm.
It has a direction. Okay, so put a star and write. Momentum has a direction. Okay, so if there is a change in potential energy, sorry. If there's a change in momentum, there would of course be a change in what, Siddharth?
Velocity.
Of course.
You can't change it.
Yeah, of course the change in mass can also create a change in momentum, like there is an explosion, there's a bomb exploding,
Yeah.
so then it separates into different pieces.
Yeah. So
And then the mass, so that is also a kind of a situation, a scenario where a change in momentum occurs.
But
Okay.
it's usually velocity.
Yeah, it's usually velocity,
Mhm.
but it can also be mass, because mass is also a variable. Okay, understand? So explosion is a good example for change in mass. All right. Okay, so let's move on to the next page. And I said momentum is a vector quantity. Therefore, the total momentum of a certain system is equal to the vector sum of individual momentums. Do you understand
Like
that?
the particles you're talking
Yes, that's right. I'll show you. Now, suppose I have, consider these particles are of one system, and this is M1, and this is M2, and this is M3, and this is moving in this direction, and M2 is moving in the opposite direction, and this is in this direction. Then the total momentum is M1 V1 negative, M2 V2 positive, M3 V3, and so on. Do you understand?
Yeah.
Yeah, so sign matters. So the direction matters, therefore the sign matters. That's why I said put a star and write the direction is important. Okay. Then calculate the moment of the following sums. Can you do that one, please, as soon as possible? The first one.
140.
Yes, 140. That's right. Then the next one. A system of two blocks, each of 4 kg in mass, each moving at a speed of 15 meters per second but in opposite directions. What is the total momentum? It's a system of two blocks.
So it'd be like
What do you think?
the sign would change. Would it be 4 times 15 and then minus 4
That's
times 15?
right. That's right.
So it'd be 0.
0. That's right. So inside that system, the momentum is 0.
Okay.
Inside that system. Okay, let's go to the next one. Interpret and use force versus time graphs. Now, before I talk about force versus time graph, I'm introducing you another important word in physics, that is impulse. Have you have any idea of what impulse is?
Like a reaction almost?
Yes, kind of. Okay, so it actually, like for momentum, it has no proper definition. It has been defined using an equation.
Mm-hmm.
Okay, so impulse, which is denoted by J, impulse, which is denoted by J, equals F into delta T. If we are applying a certain force on a certain object for a certain time, the force which is applied on that object is called impulse. Okay, I am applying 10 Newton on this particular object for 10 seconds. So the impulsive force, in other words, it's the impulsive force, is F into T.
Okay.
Okay, so that's impulse. Okay, so
Wait,
So-
why is it change of time? Wouldn't it just be force times the time you?
it can be taken as force into time, but it's simply the force into change of time.
Okay.
the change, the impulse which occurred during a certain time range,
Oh,
a certain
okay.
time period. Okay?
So within the time range something.
Yes, that's right. Okay, so actually this is coming from Newton's second law. I will quickly introduce you this. You don't have to understand that since you have not learned Newton's second law. I said Newton's second law is F equals ma. M, A acceleration is delta v over delta t. Do you know that? Difference in velocity and difference over time. So this is, if I take this delta t here, what do you get? M equals delta v. M into delta v, sorry. So what is this? This is impulse. So what do you think? What do you think this is? What do you think this is? They are asking what speed it has attained after 4 seconds. So what is the change of momentum there? mv minus, so this is 6,000, next is 1,005, v then would be how much?
4. Oh, so we used to. Okay.
Got it? Not confused?
No, I didn't. I didn't know that we used the 6,000 from the previous.
Yeah, you have to. Most of the times, if you have steps, the step above would most probably be one of the data for the second step. Okay, so keep that in mind. So those are the tricks. Okay, so that sum is over. Alright, so I want you to do, we have 5 more minutes. So then I'll be left with conservation of momentum. Shall I do it next time? Conservation of momentum?
Sure.
Yeah, the only left is conservation of momentum. I have to talk, I need some time to explain that. Okay, so let's move on to the sums. We have a couple of sums and I will give you some homework too. Okay, okay, to the second one. A 2 kg body is initially traveling at a velocity of 40 ms minus 1. Read it.
With a constant force of 10 newtons slows the body down for a duration of 5 seconds.
What
What
is
is
the
the
final
final
speed of the body?
body? What is the equation for like slowing down?
Equation for delta P equals Ft.
Yeah, momentum.
Yes.
Okay.
So delta P equals Ft is more than enough for this. Write it down. Delta P. What is delta P?
Momentum.
Yes. So why don't we draw this once again? When you draw something, you get a kind of a clear picture of your head of what is happening. Because this is just so many words with so many technical terms, right? So let's draw it. This is a 2 kg body. So it is being exerted a 10 Newton force. It was traveling at a velocity of 40 ms minus 1. And this force is slowing it down for 5 seconds. They are asking what the velocity is now. What the velocity is now. Okay, so we know change in momentum equals Ft. Now Siddhartha values. Before thinking of the sum, think of what you have. You have force. You have time. But I don't have delta P. How do I find delta P? Delta P is the change in momentum. That is final momentum negative or sub initial momentum. So I will write P final minus P initial into F T. Okay. So what is P final? Of course, the final one should be, okay, never mind. Final one is what? This is 2 MV, P is MV. So I'll write 2 straight away. It is U.
Okay.
Sub P initial is 2 into 40. So what is F? 10 into 5, 50. This would be 2 U equals 80. It should be the other way. Changing momentum initial to U. Forcing the time, yes, the direction matters. It should be the other way. Changing momentum. Change is, what is a change actually? Change is initial, final negative initial.
Yeah,
It's final.
Final
Yeah,
minus
okay, then I'm correct, okay. So 2U equals 80 goes to the other side. 130, U becomes 65. Oh no, I'm wrong. It cannot be 65. I need to think. I didn't think. We should do this sum keeping in mind that the potential, the momentum decreases. This is being decreased. So what is the potential here? Sorry, the momentum you have should be decreased when it comes here. So it should be actually the difference. So this is the lesser one. This is the lesser one, so that should be at the end. So this is the initial, this is the final. Final one should be 2U. Okay? Then this should be 80. Then your answer would be something different, and which would be the probable, the correct answer. So 50, 80 minus 50 becomes 2U, 30, 2U. So why did I decide that I'm wrong, that I made a mistake? Because I got a velocity which is more than,
That makes sense.
yeah, that makes sense. So I understood that I made a mistake. I made a mistake without thinking that the latter one is less. Okay, so those things happen. All right, so you can do you have 2 more sums. You can do them at home. I think our email addresses are given to them. Are they?
I can send you your email.
Yeah.
If you want.
Okay, so if you have any question, please do them. Go home today. You're on vacation. You don't have anything. Okay? You don't have any big work. Read this again. Take another piece of paper and write down all the important equations. Don't write definitions. Don't write laws. Okay? That won't be a short note. And then hang it somewhere. Okay? And try to do sums try to find some sums. I think he also will be sending you some sums. Okay? And for this, I want to make a small alteration. Now, this here, these are the directions of the forces.